Thank you everybody to be here today, to join us in this webinar. Today we would like to take a closer look to how the semiconductor ecosystem is structured. And we will go through all the key players shaping this industry and take some time to highlight where MoveX fits in this landscape. So moving on, I'm Ylenia Carola, Head of Business Development at MoveX, and we also have here Stefano. Hello, Stefano.
Hi, Ylenia, everybody.
So Stefano is our field application engineer, and he will hold all the more technical, let's say, stuffs of this meeting, this webinar, actually. So moving on. Let's start from this question. From the very beginning, where we can find chips. So here the answer is everywhere. Even if you don't really see them, a chip might power a smartphone or run an AI in a data center, help a car drive safely, or make sure that a medical device or a satellite works in a reliable way. Chips are in all the product that we use every day. So here we will start with the first let's say player in this market that are the clients, and not every client is the same. And what really differs them is what kind of chips they need. Some companies are perfectly fine with using general purpose components. Like off-the-shelf chips that are widely available from suppliers such as TI, STM, or analog devices. So from one side, we have the general purpose chips that are great when you need something really fast. You don't need anything specific, and your product can adapt to what's already on the market. But here is the catch, and these chips often include more functionality than you actually need, which means that you are wasted silicon area. You have a higher power consumption, and sometimes the form factors don't really match what you need. So don't really match your technical or integration needs. From the other side, we have ASIC. The ASIC that are application-specific integrated circuits. ASICs are custom designed to do exactly what you need, nothing more and nothing less. And they are optimized for size, performances, power, integration, and so on. And they are essential when you work on a space constrained devices such as the medical implants, the wearables, and all the automotive modules. Of course, there is an initial cost that is higher from the general purpose chips. And also in terms of time for the design and the development. Obviously also this part it's let's say more consistent, but if your production volume is high, your requirements are strict. An ASIC is often the most cost efficient also, and it's the more technically speaking solution. So So in short, general purpose is good for if you need something fast, flexible, and if you have a need that is for low volume. And ASIC is the best for the performances, the efficiency, and all the needs that are like miniaturization and high volume products. At MoveX, what we do is helping companies go from a concept or a technical requirement to a fully functional chip. What we do is tailor-made the chips for our client applications. So here is more or less how we work. We start by understanding the system requirements and turning them into clear technical specification. Then we study the feasibility. We check things like the cost, the area, the power, the performances, obviously all depending on the client's needs. And after that, we move into circuit design and run simulation to make sure that everything works in different conditions. So then we take care of the layout and all the physical checks. We make sure that the design is ready for production, and once everything is validated, we handle the final tip out. With all the required file sent. Finally, we also continue to support our customers in the post tip out phase. For all this part, we have dedicated a full webinar to these processes that we can also find it on our YouTube channel and in our news section in our web page. So I will handle from here to Stefano that will go on with the steps needed to production.
Yeah, thank you, Ylenia. So it's very important to see also the software part of design IC. So to properly make the design of ICs, engineers need different software and tool that can help in automatize each phase of the design. These tools are called EDA, so electronic design automation. They are for both analog and digital design, and they can cover each phase of the design. So the actual design, but also the simulation, verification, layout, and post-layout simulation. For each one, there are different tools and software. Here we can see some example for each phase. So for the schematic, for the simulation, and so on, from different provider. The major provider are here: Cadence, Synopsys, and Siemens. These are the major companies to provide the EDA tools, but also at MoveX, we have developed an EDA software called Spaceman that is a copilot available for designer to automatically size, optimize, and simulate analog IPs in a very smart and fast way, all thanks to AI. To better understand how this software Spaceman works, we had the first webinar of this series focused on its capabilities and to go deeper on its functionalities. So after the design and simulation and verification, we have the completed circuit, but this circuit must be clearly physically produced. This happens in facilities called foundries, where the semiconductor wafers are processed with nanoscale precision to make each single die. So the market of semiconductor foundries is really dominated by Asian countries, led first by Taiwan and then followed by South Korea, USA, and China. The major companies are here in the example are the Taiwanese leader TSMC that covered more than 50% of the production of semiconductor. It's followed by the Korean Samsung, and then American Global Foundries, the Chinese company SMIC, and another Taiwanese UMC. In the foundries, to achieve the final chip production, we have a lot of different steps, all quite complicated and, let's say, hard to be achieved. All starts from the silicon wafer or other semiconductor wafer. They have to be polished and prepared to be processed. Then in some steps, there is the need to cover this wafer with a thin film of material, could be oxides or metals or any other material. This can happen in different phases. What is important is that the process could be a chemical vapor deposition, a physical vapor deposition, or an atomic layer deposition, or other technique to cover the wafer with thin films of material. One of the material that we need to use to cover the wafer is the photoresist. This photoresist is needed in one of the most important steps in the production, the photolithography. During this step, the circuit patterns are projected on the wafer so that in the successive phase during the etching, by exploiting some chemicals, all the not necessary material can be removed in a very precise way. Other steps regard the doping of different zones in the wafer for each die to achieve the creation of N-type and P-type silicon with the successive formation of the actual transistor structure. At the end, we need to build also all the interconnection between the devices that are made with the metallization by deposition of metal like aluminum or copper lines. All these steps can be made in different times during the production to achieve multi-layer wafers. So we have just seen how the typical process of fabrication of ICs is made, but actually there exists many different technology available. So the most important parameter in a technology is represented by the node dimension. So that means the minimum length of a gate, of a single transistor gate. Year by year, we developed smaller and smaller technology, making available to integrate many more transistors in the same area. Today, the most advanced technology are just a few nanometers size, in some cases even 1 single or 2 nanometer, but today actually the name is more marketing related than the actual minimum length of the gate. In any case, to achieve so small size of devices, the standard planar technology of MOSFET is no more sufficient. So from about 20 nanometer of length, we need to change the technology to the FinFET, which is no more a standard planar transistor, while it's now a three-dimensional gate and transistor structure. And then to achieve even more scale node around the 3 nanometer side, we need to develop an even more advanced type of transistor, which is the gate all around the FET. These types of devices allow a very higher integration of transistor in a small area, a very advanced performance and so on, but they also bring particular issues in the design in terms of complexity. They add new challenges to be managed, and also they need a more advanced machinery and a more complex process to be properly fabricated. So together with the different technologies, we have also the PDK, which is the process design kit that is a fundamental part to properly design each circuit. The PDK includes all the necessary design rules, the physical model of each single device, and it allows the engineer to actually design in the specific technology each single block. It's the fundamental kit to make the design, but also all the simulation and verification step of each single circuit, and it's given by the foundry together with each single different technology node. Finally, as we were talking about advanced transistor like FinFET and gate-all-around FET and different technology node, it's very important to make a mention on the machinery we need to fabricate these devices, in particular for what concerns the photolithography step, which is the most advanced one. In particular, for photolithography of advanced node, we need extremely high precision machinery, ultraviolet machinery. They worth about different tens or maybe also hundreds of millions of dollars each, and they need to be exploited to achieve nanometer precision lithography. And it's important to notice that only one company in the world, ASML, based in Netherlands, has the technology to produce extreme ultraviolet lithography to make so scaled node of FinFET. This is very important because it's an European excellence in the semiconductor market and one of the key points to achieve the most advanced FinFET IC technology. So we have seen how complex is the procedure of fabrication of ICs, but the path from design to market is not finished yet. And Ylenia will tell us what's next in the path for a single chip. Yle, you're muted.
Just 1 second. So here we are. So, like Stefano was saying, once the chips leaves the fab is far from ready to be to hit the market. We need some more steps. In particular, we need the testing, packaging, and validation steps. Let's start from the testing. So testing is the first step, and they test the chip while the chips are still on the wafer, and then again after it's been packaged. Basically, they are checking to make sure everything works properly and there is no electrical issues or broken connections. Sometimes the chips might fail because of a short circuit or maybe for a time problem. And when that happens, what they normally do is take it out, and if it still kind of works, it might be used in a less demanding product. These are tests. These tests are done using special machines that can spot problems in just a fraction of seconds. Major players here are Teradyne and Advantest. Next, we move on packaging. A step that might seem like secondary, but is actually super important. Packaging is not to be think like just a box around the chips. In fact, it plays a big role in making sure that the chips work well in the real world. And as the technology moves forward, packaging is becoming a field of innovation too. It has three functionality. The first one is the protection. It keeps the chip safe from the damages, humidity, and dust. Then also the connection. It allow the chip to communicate with the rest of the system using tiny wires or bumps. And also the cooling. So it helps the chips get rid of heat, so it can be more reliable. For high performance chips, like the ones that are used in AI or in fast computing, chips, the packagings are also they are also affecting how the signal move and how the power is used in an efficient way. There is why there is a lot of going on about innovation in this field, and some of the major players are ASE, TSMC, Amorc, and so on. Amcor, and so on. Then we move to the last step, that is the validation. So validation is when the chip is put into a real system or a board, and it's tested in a real world situation. It's like checking is if everything works well together. Like, does the chip work correctly and follow all the rules? For example, a chip might pass the earlier stage, the earlier test, but still fail when it gets too hot or doing maybe electromagnetic test. So in this phase, small problems might only show up when the hardware and the software are used together. So companies like Integra Technologies focus on this step, especially for industries like the aerospace or the defense, where everything must work perfectly. Only passing all these steps, a chip is ready to be used in things like phone, cars, servers, satellites. Here we come back to the first slide and the first thing that we have said. So the customer, after testing, packaging, validation, the chip is finally ready to be integrated into real devices. Okay, so this same chip can do many things, like it could be maybe be the power of the newest smartphone, or like we said, run an AI task in a big data center, or maybe can also help cars drive in a safely way. I think in this point we have covered pretty much all the chip journey, from the first idea to being built in a factory, to be tested also. That's pretty much. I hope you understood more or less what make the semiconductor industry something amazing, because it's complex, it's full of teamwork, and it also affects mostly every industry, even if most of the people never see a chip itself. So the last thing we need to do here is to move, let me see, forward to the Q&A session. I think we have received already some questions.
Yes, I see one question here related to the technology side. So the question is, you have talked about different technologies. Which one have you used in MoveX? So I guess here we were talking about the different technology node. We explained in some of the slides. As MoveX, we work in different field of IC design. We are focused first on the power management side, so developing a PMIC and converter for power application. This is, generally speaking, is more into not so scaled technology. So we exploit a lot different BCD technology around 110, 180, 130 nanometers. So not so scaled, because we are talking about power components, which are quite bulky and not so, let's say, scalable. But we have a very good experience also related to standard CMOS technology in around 65, 40, 28 nanometer. And in the last years, we started also to work in a very advanced node. And we had the chance to work on a couple of FinFET node around 3 and 5 nanometers. So actually, in MoveX, we have quite a wide view on different technology, and we have quite a good experience in a lot of different nodes, also from different foundries. Because the point is that there exist different technologies, different nodes, but they came also from different foundries, so that they can have different flavor of devices, different performance, and we had the chance to give a look and try different nodes from different fabrication plants. I see we have also
something
one
else?
more question. This time is related to the EDA, and they ask, so Spaceman is an EDA you developed as an alternative for the most common like Cadence or Synopsys. No, because yes, Spaceman is an EDA, but it's not an alternative for the Cadence one or Synopsys one. It's more an EDA to be used together with the other tool. We work a lot with Cadence, but generally speaking, Spaceman is meant to be used as a tool, not to make the whole design from scratch, but to automatically make the sizing and the optimization and verification of already existing schematics. So Spaceman will completely fasten up the process of sizing and designing, but it has to be used together with the other EDA providers' software.
Okay, so we have the last one that is which applications do you target using the more advanced node?
Yes, since in the, let's say, not advanced node, we use them to achieve power management, power converter application. For the most advanced node, we are starting to work on some, let's say, high frequency circuit, high frequency ICs, and so on. In particular, for some communication IP and ICs. In any case, we work with in this advanced technology for our customers, so approaching their application. Generally, we developed some IP to be using their ASIC into way. First, we work on their, let's say, high frequency IPs, and then we also use these nodes for the power related part of these chips, because even if you are using a 5 nanometer technology in the chip, there will be some power related IP. And since we have a very good experience on that, we can help also the customer on that part. Also, because it happens quite often that to work on a highly scaled node, you need a very specific knowledge, a very precise experience in that types of devices that are used for high-speed circuitry, so that maybe the power-related part is not your focus, so we can help there. But we are also designing some advanced communication circuitry exploiting these nodes because they allow higher frequency and higher performance.
Okay, thank you so much. So I will say that that's all for today. You will find the recording of this meeting on our YouTube channel. Feel free to contact us to info@movex.it or directly to me or Stefano. Thank you so much.
Thank you, everyone.